Welcome to the next lecture in data formats. Today we are going to talk about yet another graph data model called labeled property graph and a graph query language called Cypher, which works on top of the labeled property graph. So up to now we were talking about the resource description framework RDF as a graph data model, and today I'll introduce you to another graph data model used quite a lot. Before we get to the labeled property graph data model, let's revisit the notion of a graph and data as a graph, and what does it mean to represent data as a graph, and why would we do that? When I was talking about the RDF data model, I showed you how it is easy to get from the conceptual data model to a graph data model such as RDF, because the conceptual model models what is around us, models the real world objects and their relations, and then the graph data model does basically the same. Today I'll start with another angle of introduction of representing data as graphs. So first, let's start with what is a graph. A graph are discrete entities and their relationships of various types. That is what we already know. And the question, why use graphs for data? Well, this has to do with the question, why do we collect data? Well, we collect data to record what is happening in the world around us. And how do we do that? Well, we create a representation of the reality that is happening around us. And what is the reality we represent? Well, often enough, it is things around us and how they are connected. That's why the graph data model is the most natural data model for representing data and the reality around us. And this is because almost anything can be a graph. It can be infrastructure. You have islands and you have connections among those islands which represent bridges, or you have molecules made of atoms and their bonds, or for instance the internet in many different ways represents a graph. You can have the metallic cable paths where nodes are switches and edges are the cables. Or you may represent networks as a graph, where nodes are servers and clients, and edges are representing that a client is served by a server. Or you may represent pages on a website in a graph, where nodes are the pages and edges are the links from one page to another. And that's not all. You have social networks, a very famous and current and frequent use case for representing data as graphs, where nodes are people and edges are friendships of those people. You have money traces, where nodes are companies or individuals and their accounts, and edges are money transfers. And then you have permissions. Nodes are resources and users, and edges are permissions to read, to write, to execute something, and so on. Now, the graph data model is often compared to the traditional relational data model. And let's have a look. So we want to represent in our data that John has bought a V60 coffee. In the graph data model, we have a node for John, we have a node for the V60 coffee, and we have a relationship that says that John bought this type of coffee. Now, in the relational model, we have to fit our data into rows and columns, which itself is not natural because things and their relationships don't appear around us shaped like tables and rows and columns. We do that for good reason, for optimization, to avoid redundancies. And if we have lots and lots of data in one table, then a table is a good optimal representation for such data. But this holds only for use cases where we do not have to do many joins in SQL then, so we don't have to connect many of those tables. Once we do, it is an indication that we might be running into a graph-shaped problem. On the other hand, not everything is suitable to be solved by a graph data model. For instance, when we have a log of sales or maybe a list of beverages sold, and we want to ask questions like what is the turnover of a company, or what is the average profit margin, or what is the most popular product. Those questions involve summation over the whole table and maybe join of one or two or three tables. For that, if we have lots and lots of data, the relational data model is the best one there is. But let's take a look at some of the problems and use cases for graph data. One of the most prominent use cases for graph data is the one where you realize that in your data, the connections between entities are as important or even more important than the entities themselves. There is a rule of thumb, again comparing to the relational data model, that is saying that when you often enough write SQL queries with multiple joins, and multiple means 5+, then you might be looking at a graph-shaped problem, and it might be better for you to think about using a graph data model, a graph database for storing and using your data. For instance, in this example, we have a question: what professions will have reduced selection of coffee in their coffee shops when there is a drought in Colombia? Well, to be able to answer that, we first need to know what producers of coffee are located in Colombia. Then we need to know what types of coffee they produce and where this coffee is served at, who visits such coffee shops, and where do those people work. When we have all this data connected like this, we are able to answer this query, and we are happy. But imagine having all this data in a relational database. It would be lots of joins. Another graph problem and a good use case for graph database is when we have self-referencing, which means in SQL you would have a table, and to answer your query you would have to join this table with itself many times over. So this is management hierarchies, family trees, and so on. In that case, it also might be better to actually use graph data model for your data. Another use case is when there are hierarchies, and at design time you do not know how deep you will have to go in your graph to be able to exploit those hierarchies to answer the queries. For instance, if we would have a network of switches, and we would like to know which parts of the network fail when one of the switches fails, then we don't know how deep we'll have to go in the graph at design time of a query. So it is hard to write queries like this. The same type of use case is when you model distribution networks and you want to know what happens if one business closes. For instance, in this example, we have a gold mine which sells gold, and the gold is bought by an electronics manufacturer who sells processors. And the processors are bought by phone manufacturers who sell phones. And the phones are bought by the gold mine to be able to communicate with the workers in the mine. Well, when the electronics manufacturer closes down, no one wants to buy the gold from the gold mine, so that's a hit for the gold mine. Then the phone manufacturer doesn't have processors to be bought, and therefore stops producing phones, and therefore the gold mine has no one to sell gold to and has no one to buy phones from, for instance. This is, of course, a very simplified example of a distribution network. Now, the same goes for permissions on resources. So you have a hierarchy of resources. For instance, in your file system, you have folders, and you want to change a permission on a folder, and you want to know permissions of what you need to change as well. So you need to go into the folder and see what files are in there and other folders in there, and open those folders and go and again and again and again, and you don't know how deep this hierarchy is when you are writing your query. So this is also a graph-shaped problem, when you don't know how deep you need to go when you are writing your query. Another example of a graph-shaped problem is when you need to discover many different paths between your source node and your target node. So this is typical for route planning, for public transport, or maybe for goods delivery, or maybe for redundancy detection, when you want to know how many disjoint paths are there between node A and node B, so that if something fails, you have another path of how to reach node A from node B. Here again we have an example from public transport from Prague. We want to go from Můstek to Florence, and there are many different ways how to get there, and now the query might ask for which one is the shortest, and the shortest might be defined differently. The shortest path might be the one with the least nodes on the way, or the least edges, or it might be the one that takes the least time, which are two different things. So those are graph-shaped problems. Right, so when you discover these problems, you know that you should consider using a graph data model. Which one is still unclear, and we'll get to the comparison of the labeled property graph data model and RDF at the end of today's lecture. But first, let me introduce the labeled property graph data model. One of the prominent companies working with labeled property graphs is Neo4j, and one employee of that company says that the whiteboard model is the physical model, which is the advantage of the labeled property graph. What does he mean? Well, imagine that you are in a conference room and you talk to business people from your company, and you talk about your new system you are going to build and how the data in that system will be structured. So typically you'll draw on the whiteboard entities and how they are connected, and what Ryan Boyd says is this, what you draw on the whiteboard, is what becomes or how the data is then structured in your graph database, and it is the same model of how the data is then structured on the disk, the physical model, when you use Neo4j, which is one of the most prominent databases implementing the labeled property graph data model. Now, what do we work with here when we have the labeled property graph data model? Well, we'll have James and we'll have John, and we want to say that James follows John. So James and John will become nodes in our graph, and follows will become the type of the relationship that we want to represent in our graph. The relationship is directed, which means that the fact that James follows John is something different than when John follows James. So if they both follow each other, for instance on Twitter, then there are two relationships in that graph, one in one direction and one in the other direction. There might be also another type of relationship we want to have in our data, for instance, that James works with John. This type of relationships typically is symmetric. So when James works with John, it might also mean that John works with James. But still, the property graph data model only works with directed relationships. Right, so now we have talked about the graph. nodes, and relationships. Let's add the properties. James will have a name, James, and age 32. And John will have a name, John, and age 42. And John will also have a Twitter handle, John. And James doesn't have one, but this is okay because each node may have a different set of properties in the labeled property graph data model. Now, James owns a camera. A camera is another node, and owns is another type of relationship. And the camera has a vendor, Panasonic, and a model, TMC DS30A. Now, James not only owns the model, the camera, but James also uses the camera. And John also uses the same camera. So that's another thing we'll have in our data. Now, what's different in the labeled property graph data model, what we couldn't do with RDF, is that the relationships themselves also have properties. So here we say that James owns the camera since Christmas 2020 and uses the camera also since Christmas 2020. John, on the other hand, uses the camera since January 2021 when James got to work and showed off his new camera. Now, those are properties in the property graph data model, and we are talking about a labeled property graph data model. So for that, we'll add the labels. Nodes can have labels. So the labels are used as types of nodes. So James is a person. John is also a person. And the camera is a camera, and it is also an electronic device. So the nodes in the graph can have sets of labels. The relationships, on the other hand, have only their type, which is the label of the relationship, and they have only one. Now, another advantage of the property graph data model is that the data in that model can be read in English quite easily. The labels of nodes are nouns. The properties are adjectives. So we'll have a person whose name is James and his age is 32. So James, the person is named James and is 32 years old, adjectives. The relationships are verbs, and the properties of those relationships are adverbs. And that's it. Simple mapping to English. So the labeled property graph data model is an oriented multigraph where nodes have sets of labels, edges have labels, and nodes and edges have sets of key value properties. Now we'll talk about Cypher, a query language for the labeled property graph data model. And we'll start with a simple example. We'll create our first pieces of data in the labeled property graph data model using Cypher. And here we'll use the create statement with the keyword create. And then we'll want to create a node defined by those parentheses. The node will have a label or a type person, and we'll have properties, actually one property name with the value James. And the properties are specified in a JSON-like syntax inside the parentheses denoting the node. And then we'll want this node to be connected using the follows relationship to another node. And the other node will also be a person with a name John. Now, after issuing this statement where we have the labels and the properties, the data is created. So two nodes are created, one named James, one named John, both of a type person, and a relationship between them, actually going from James to John, of a type follows. Now, static data can be created this way. Note that the query looks or uses ASCII art, so it looks a little bit like the drawing of the graph. So the nodes are denoted by the round parentheses, and the relationship is denoted by an arrow on which you have the follows type in the square brackets, which resemble the rectangle that is visible on top of this slide. So Cypher aims at being readable, and yeah, they call it ASCII art for graphs. Now let's take a look at our data where we have James and John and their camera, and we want to ask, who uses a camera owned by a followed person? Well, here we use Cypher and we'll use the match keyword. So we'll match a pattern that looks like this. We have a node of a type person. We'll want to save the instance of the found node as a variable p1. So p1 here is a variable. Now, this person p1 uses a camera C, and camera C is owned by a person p2. Here note that the arrow can go the other way around and it still works. So we can say that the camera is owned by and denote it as the camera, the reverse arrow with the owns type of the relationship, and p2 person. And the p2 person is followed by the first person p1. So person p1 who uses the camera, who is owned by person p2. So person p2 obviously in this database is James, and person p1 who also follows James is John, and will return John. So p1, c, p2, and p1 here are variables in Cypher query language. So these were really simple examples of Cypher for creating data and querying the data. The Cypher query language was created by Neo4j. Neo4j is both a company and their product, Neo4j, the graph database. Initially, each graph database vendor had their own query language, so Cypher was the query language of Neo4j. Recently, this situation got a little bit better because via the Open Cypher project, also other vendors of graph databases joined in and implemented Cypher as a query language for their graph databases. So Oracle, Tableau, Databricks, who are behind Apache Spark, and SAP HANA all implement Cypher thanks to the Open Cypher project, which means that Cypher is no longer a query language of a single graph database vendor, and that is why we are talking about it today. Now, Cypher aims to use ASCII art. So the queries in Cypher aim to be readable as ASCII art for graphs. So that's why nodes are represented by the round parentheses, and labels, which represent types, start with a colon. So we can read it as a P, who is a person, who is a mammal. And the properties use a JSON-like syntax, which is a simple key value list of properties. And relationships can be written as arrows, where we either don't care about the type of the relationship, then we just use the arrow, or we do care about the type of the relationship, and then we specify the type of the relationship inside the square brackets in the middle of the arrow. And if we want to save the found relationship instance into a variable, we specify the variable as with the nodes. So in the brackets, both for nodes and for edges, first goes the variable and then a type, and in case of nodes, there may be a list of types. Now, the direction of the relationships can go both ways. We can go from P1 to P2 or from P2 to P1, still writing P1 first and P2 second. So we can go through the direction of the relationship or against it, and still the query is quite readable. And we have seen this in one of the previous examples. And what is the most visible advantage of the property graph data model is that even the relationships can have properties. And if a relationship has properties, they are written inside the square brackets the same way as with nodes. So again, P, P1, P2, and F here are variables. Okay, so let's get back to querying for a bit. Now let's find James's camera. So here we'll use again match, and we'll want to find a camera C, which is owned by a person named James, and we want to return the camera C. So like this, we find James's camera and return it in a variable C, which will contain the representation of the node. Now, this may be written in another syntax using the where clause. So we may match a camera C owned by a person P and then use the where clause where we'll access the property name of the person P, and we'll say that it needs to be James, and then we'll return C. So this is an alternative syntax to matching the properties and values. Now let's introduce the set clause. Once we have the variables matched, we may add some properties and values into those variables. Like here, we'll match the camera C, and then we'll set the condition property on the camera to used. And only then we'll return the representation of the camera. And again, there is an alternative syntax where we can use the += operator to merge the properties and values using the JSON-like syntax into the node represented by the C variable. And the result is the same. The returned node will have the condition property set to used. Now, it may happen that in my company, I have multiple people named James. But let's say I do not want that. Without anything, Cypher will allow us to have multiple nodes in the property graph named with the same name or identified by the same name. So if we want to prevent that and to say that in our company only one person can be named James, we need to put a constraint on the type node type person. So we can do that like so. We create a constraint on P person, and we say that the P name needs to be unique. So now, if we already have a James in our database, and there will only be one because of the constraint, when we issue a create statement like this, we'll create a node of a type person, and the name is James, we'll get a constraint violation. So we no longer can create another James because we already have one. Now, we want to add some relations to James. So we create a person named James, and we create a relationship saying that P, the person named James, owns a laptop sold or made by Dell. Now, if we issue the query like this, we also get a constraint violation. And this is because James, in this case, already exists. So it is the same reason as before. Because James already exists, I cannot issue this query. So this is a bit inconvenient because I'm sometimes not sure whether the node I want to be part of a relationship is already in the data or not. So if I want to be sure that the query runs either way, so either there is already a James and then he's not created again, or there is not a James and then he gets created, I change the create keyword to merge. So merge works like this. It first tries to match what is to be created, and if it matches, then nothing happens. if it doesn't match what is to be created, in this case the person named James, it creates the person named James. Either way, it works. And then the relationship can be created. So this query actually went through. And now this query can be extended a little bit, and we may say that we want to merge a person named James, and if there was no James, so the merge resulted in a create, then on create set this person's Twitter handle to James. Note that the relationship creation also got changed into a merge, which means that if there was a relationship like this before, nothing gets created. Now, the variables that we have seen so far contained nodes or contained relationships. In Cypher, the variables may also contain whole paths. So here, the path will be from a person to a laptop through the owns relationship, and the whole path may be returned as a content of a variable called path. Another thing which may come in handy is that in Cypher you can query the data without knowing the exact direction of a relationship. We had an example where we had James who works with John, and the relationship was in this direction. So James works with John. But if I am a user who wants to query this data and does not know in which direction the works with relation is in the data, it is possible to query for the relationship disregarding the direction. So if you look closely, this arrow representing the relationship actually is not an arrow. It's just two dashes, meaning that it doesn't matter in which direction the relationship is, and it still will match. And here we return star. Star means the same thing as in other query languages, so it returns all variables used in the query. So it will return P1 containing a person, P2 containing a person, and a W containing the relationship. Now, it is important to say that since the relationship in the data actually was created with the direction from James to John, it also gets returned in the W variable with this direction, even though we query it in the other direction. We query it from, or John was first in the query and James was second, but since in the database James is the source and John is the target of the relationship, it gets returned with the direction as stated in the data. Now, this is also the first time I show you the Neo4j query browser, where you can issue queries and see the results. Now, there are two main modes of seeing the results. The first one is if the result contains a set of nodes and relationships, it will get rendered as a graph. If the result contains just strings, it gets returned as a regular table. So in this second example, we match John, who works with another person, and we want John's name and the other person's name. So those are two strings, and those get returned as a row in a results table. Whether in the first case, P1 contains a node, P2 contains a node, and W contains a relationship, which can be rendered as a graph. At this point, I want to mention that Cypher has a style guide. This style guide basically says how to syntactically write Cypher queries so that they are easily read by other people. So this style guide actually contains a lot of rules, so you may want to go through it if you are going to create Cypher queries and share them. But the basic rules are that node labels should use upper camel case, which means that they are beginning with a uppercase character, and then when they are multi-word phrases, there are no spaces, and each word starts with an uppercase character, which means that the vehicle owner node type should be written as in the first case and not as in the second case. For relationship types, the rule is that it should use the screaming snake case, which means everything uppercase, and instead of spaces there are underscores. So owns vehicle should be written as in the first case and not as in the second case. And there are also rules for property keys, which should be lower camel case, and Cypher keywords, which should be all uppercase. Even though keywords are case insensitive in Cypher, it is just good style to write them all uppercase. But let's get back to querying for a bit. Once we have our paths and variables, we may want to aggregate the resulting values, as in every other query language. So, for instance, we want to count the number of movies a specific actor acted in. So we'll match the path from a person to a movie of a acted in type, and we want to count the numbers and group by the person's name. In Cypher, there is no need for a group by keyword, because all non-aggregate fields, like pname in this example, are used for grouping implicitly. So because in the return we have count star, we know that there will be aggregation, and the only non-aggregate field is pname, which means that the query will be grouped by pname, and we'll see the count of the numbers of the movies in the number of movies variable. So the result will look like this. Now there is a large amount of various functions for aggregations, for working with strings and dates and so on. And for the list, I'll refer you to the Neo4j Cypher ref card, which may come in handy when working with Cypher. It looks like in the slide, so it is a concise list of functions implemented in Cypher, and a short description, and yeah, you may use this as a cheat sheet. Now, when we have our results, we may also want to filter them. So for instance, we want to see a person who acted in a movie, but we want results only for movies released after the year 2000. We may do that in the where clause, where we specify the logical expression that needs to evaluate to true for results that get returned. So here we return the title of the movie, the year released, and the name of the actor. Now, in query results in Cypher, you may come across a null value. Now, the null value means that the value does not exist for the specific result. The null value itself never gets stored in the database, because when a value is missing, it is just not in the database. So this is the same as with Sparkle, where we had the special not bound value, which also was never stored in the data, but it was the value of a property when the property was not bound to any value. So in Cypher, there is the null value for this. But it is different from SQL, where in SQL, in relational databases, the null value actually is stored in the table whenever we don't know a value. So in the graph data, there is nothing like a null value, only in the results of queries. Now, we may also want to use regular expression matching when comparing strings. So for instance, here we want people who acted in movies whose name starts with T and the movie was released after the year 2000. So in this case, we'll get only those movies in which actors whose name start with T acted in. And we also see the usage of a Boolean connective AND in the query. And of course, there are the other ones present in Cypher as well. So that is OR, XOR, and NOT. Now, sometimes we need to manipulate the result a little bit before we actually return it. So that's what the with clause is for. So here we match N, a person, and with that person, we order the results in a descending way according to the name, and we take the first three. And then the first three are fed to the collect function, which basically takes different results and makes one value of a type list out of those results. So the result returned here is a value of a type list, which contains three values, three names of a person. Now, a second example of the with clause. Here we match David, whose name is David, and David is connected to another person using any relationship, and the other person is connected to some other node, again using a relationship, the type of which we don't care about. Now in the with clause, we take the other person, we fixate the other person, and we count all the results. So what this does is that we have David fixed and we'll have the other person fixed. So it will count all the connections going out of the other person node. And we'll call this the fourth variable, and we'll return the other person's name only when the other person has more than one outgoing connection. So that's what this query does, and it shows us that we may match some variables, and then using the with clause we may do some other operations with the result before we actually return it. Now Neo4j allows us to actually load CSV files, which are tabular files, into Neo4j using Cypher. So when we want to load data from a CSV file into Neo4j, we first need to put those files into the Neo4j's import folder. And then we want to make sure that Neo4j can read the data, and we can do that, for instance, by counting the rows in the data. And for that, we may use the following syntax: load CSV, which activates the CSV loading function, with headers, which means that the values on the first row will be used as names of properties of the row variable in which the row will be stored. So the row variable represents a row and as a node, and it has properties named by the column names, basically from the CSV file. And we will return count of those rows. If this query returns something reasonable, like the number of rows in our CSV file, then we may continue, knowing that Neo4j can read the CSV file. So then we might want to see a few rows. So we'll load CSV with headers, that's the same. Now the URL of the file here is actually relative to the import folder of Neo4j. Neo4j will not access your whole file system, it will only access the import folder. And now we'll want to return the row, and we want to limit only the first 5 rows so that we can see whether the import works. And if we see 5 rows, then we are content and we might continue. Then another thing to note when loading data into Neo4j from CSV files is that everything is a string, which means that if we want to use another data type in our data, we need to use a constructor of that data type based on the string value that comes from the CSV file. Now in the fourth query there is another difference. We don't use the with headers here. because we presume that, for instance, this file does not have headers. In that case, we cannot use the header names as names of properties on the row variable, and therefore we need to treat the row variable as an array and access those properties using those indexes of those columns. So here what happens is that we load the products CSV file, and the first value, which is at the 0 index, gets converted into an integer and stored in the product ID variable. The second column, which is the index 1, is a product name, so that remains a string. And then we have unit cost, and we want to create a float data type out of that, so a floating decimal point number. And we'll return these 3 variables, and we'll limit ourselves to the first 3 rows of the CSV file. So this query shows how to convert data types and how to load CSV without a header. And yeah, and if this works, we might continue with another query, the 5th one, where we show how values coming from columns, which might be named in a weird way, which can be used as a property name, for instance, when the column name contains weird characters or spaces, then we need to access those using the backticks notation here. So row dot backticks ship country. Ship country should work even without backticks, but if it was ship space country, then we would have to use those backticks, and we'll name this the country variable. Now we'll load the order ID and the ship country variables, and we'll try to create an order with this order ID in our database using merge, because we don't know whether this order with this order ID is already there. So if it is already there, nothing happens. If it is not there, it gets created. And we'll set, in either way, if it's created or if it's already there, we'll set its ship country property to country. And on top of that, we'll return the number of orders processed this way. Now, the merge keyword is used with load from CSV a lot, because, for instance, we might have our relational database split according to individual tables, and we don't know whether, for instance, an order is mentioned in one table and created when this table gets loaded into the database, or whether it is created when another CSV file is loaded into the database. So using the merge keyword here is safe. When the order already exists, nothing happens. When it does not exist, it gets created. Also, when, for instance, loading of the CSV file fails after 10 rows, we fix something and we want to run this query again, we don't have to delete the already created orders, because those get merged and the new ones get created like this. So merge is very useful here. And this gets us to a full Cypher query for loading a CSV file. So here, one other syntactic feature of Neo4j, we might want to avoid loading a huge CSV file in one transaction. So we may specify that the commit should happen, for instance, every 500 rows, like this. So we'll commit every 500 rows, and we'll load a CSV file with headers. We'll convert product ID, order ID, and quantity into integers, and we'll create nodes of type product with this product ID. We'll create node order with the order ID, and we'll create a relationship going from the order to the product of a type contains, and we'll assign property and value to this relationship. We'll assign the quantity ordered as a value of this relationship, and we'll return the count of relationships created. So this was a very quick overview of Cypher, just to get you started working with Neo4j or any other database that implements Cypher. And there are quite good resources that you may refer to for further reading. There is also a Neo4j YouTube channel, which I recommend. It's full of tutorials, and also this lecture was based on some of the tutorials present there. Now, the graph technology landscape in 2020 is quite extensive. In this visualization, in the top left, you can see a rectangle filled with graph DBMSs. So those are graph databases, some of which are based on the property graph data model. On the other side of the first rectangle, there are RDF databases. So those are database vendors who create databases based on the RDF data model. And in between, you can see graph databases based on a multi-model approach, where the graph database implements multiple logical data models to suit various use cases. And then there are some graph processing engines and platforms for representing or working with graph data. There is a lot of companies working on graph visual analytics, and there is lots and lots of parties interested in graph technology, both based on the labeled property graph and RDF, and maybe something in between. There is also an overview of books related to graph databases you may choose from. And one thing worth mentioning is that there is a ISO standard being developed for GQL, which should be the standard graph query language in near future. It is built on OpenCypher and other graph query languages, PGQL, GSQL, and GCore. And the GQL standard language aims to take the best of all those languages and integrate it into one standard language. The effort to create the GQL standard was started in 2019, and they aim to have the standard ready by 2022. So we'll see how this goes, and maybe in a few years we'll have a GQL standard query language for graph data, as we have SQL as a standard query language for the relational data model. Now, before we finish with today's lecture, let me just make a quick comparison of the two graph data models that we talked about in this course, and that is the resource description framework and the labeled property graph. Now, both of them are graph data models. That is clear. But each one is a little bit different and focused on different kinds of use cases. The resource description framework, RDF, is made for usage on the web. So it is made primarily for distributed data and for data publishing and for proper description of the meaning of the data. So it supports global identification of entities and predicates using IRIs, and it uses globally reused and created RDF vocabularies, which explain the meaning of the data so that other data publishers can understand the meaning of the data using standard vocabularies. And it is focused on linking data from various publishers. So it quite naturally supports that an entity from one dataset links to an entity from another dataset published by another publisher, and all the data is accessible via HTTP through the internet, and the data is on the web. On the other hand, the labeled property graph is made for centralized graph databases. So all the nodes and edges, relationships, are identified only locally within one database. So every database instance uses, for instance, different relationship types and node labels. So there is no semantic description of the data in the graph database that could be reusable among different databases. And there is no aim of the data in one graph database to be somehow integrable and or connected to data in another database. There is no aim at this. But there is a advantage to using the labeled property graph and those graph databases, and that is they are better at evaluating graph algorithms than Sparkle on top of RDF. For instance, when you want to solve the shortest path algorithm, it's directly implemented in Cypher and in Neo4j, so it's quite easy to write such a query. But finding a shortest path using Sparkle is quite challenging. Of course, the same data can be represented both in RDF and in labeled property graph. But again, depends on what you have in the data and how you model the data. For instance, remember that in RDF, we had this issue that we had an RDF triple. A page was created by and a name of the creator, and we wanted to say something about this statement. For instance, that it came from a certain web page or that it was scraped on a certain date. And we had no way of representing this in RDF other than reification. However, in the labeled property graph, the same data gets represented quite naturally because the relationships can have properties as well. So the same data, even with the metadata, is represented completely naturally in the labeled property graph because we have an entity which can have a name. For instance, this can be the URI of the page, and then we have the creator who also has a name, and the relationship created by, and the relationship has the metadata on it. So this relationship came from a website and was scraped on the 23rd of April 2020, for instance. In RDF, if we wanted to represent the same data, we had to go for reification, which meant that we took the original statement and we approached the main problem that we had, that the statement didn't have any identifier. So we out of this statement, we created an RDF resource, an entity. And we said that this resource is a statement, and we pointed to the subject, to the predicate, and to the object of the original triple. And then, since we had the entity representing this statement, we could then add the metadata. So we had the triple was created on the date, and the source was, for instance, this web page. So what we did was that we changed the triple into 4 triples, and then we added more. However, we managed to represent the same data as the labeled property graph. Of course, it is given that querying such data using Sparkle is more difficult than querying the property graph data using Cypher. That is true. And the community around RDF is well aware of this. And this is why recently there is an emerging technique called RDF star. RDF star is an extension of RDF which allows us to have a triple as a subject or an object of another triple. Syntactically, there are the 2 lower than and greater than signs, and inside those there is the embedded triple, which is used as a subject of another triple. So here the first triple says Bob states that there is someone named Alice. There is someone named Alice is the embedded triple, and it is used as a subject of the other triple that says that this is stated by Bob. And when we use the triple as an object, it is shown by the second example. So here we have employee 22 who claims that employee 38's job title is assistant designer. So employee 38's job title is assistant designer is the embedded triple, and this triple is used as an object of a triple that employee 22 claims that employee 38's job title is assistant designer. So as you can see, this is a bit similar to the reification. However, it is weaker because the embedded triple can only be used as a subject or an object of another triple. However, syntactically, it's much more readable. If we rewrote the data in RDF star, we would end up with something like this. The page created by the name of the author has a source and was created on some date. So now this is a much more much more readable representation of the data in RDF star. And RDF star represents a step towards the labeled property graph data model in the world of RDF and the web. And there is also an extension, appropriate extension of Sparkle called Sparkle Star, which allows us to query the data written as RDF star. So again, there is the same extension, and we may use everything that is in the embedded triple in the Sparkle query. So for instance, here we may filter in the query by a variable which can be used in the embedded triple. So this is all for today's lecture on the labeled property graph data model and its comparison to RDF.